January 4, 1945. Kobe Airfield, Formosa. Lieutenant Charles August coaxed his crippled Hellcat toward the first flat surface he could find, his Pratt Whitney R-2800 losing power with every passing second. The 18-cylinder radial that had carried him through 42 previous combat missions was failing, hemorrhaging oil pressure, and he had no choice but to put the 15,000-pound fighter down on enemy territory. The landing was controlled chaos. Bureau number 71,441 skidded to a halt near the Japanese airfield perimeter, its massive engine finally silent. Within minutes, Japanese ground personnel swarmed the aircraft, their shouts carrying equal parts excitement and disbelief. At Yokosuka Naval Air Technical Arsenal, Chief Engineer Lieutenant Takeshi Yamada received the message 3 days later. Americans have delivered us their most advanced fighter. The Grumman F6F Hellcat represented everything Imperial Japanese Navy engineers had been trying to understand about American aviation supremacy. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. For 18 months, this single aircraft type had systematically destroyed Japanese air power across the Pacific, achieving kill ratios that seemed to defy the fundamental principles of aerial combat. Japanese pilots reported encountering an American fighter that refused to play by the rules their Zero fighters had established. It couldn't outturn the legendary Mitsubishi A6M. It shouldn't have been able to climb with lighter Japanese designs. Yet somehow, American pilots flying this heavy, brutish machine were winning air battles at ratios approaching 20-1. Engineer Yamada walked slowly around the captured Hellcat on the morning of January 12, 1945. His technical team gathered in the cold winter air of Yokosuka. The aircraft sat on its belly, landing gear retracted, olive drab paint showing scrapes and burns from its emergency landing. American national insignia remained partially visible beneath hastily applied Japanese Hinomarus. What struck Yamada immediately was the fighter's massive size. The Hellcat measured 42 feet 8 inches from wingtip to wingtip, with a fuselage stretching 33 feet 7 inches. His Zero fighters measured 39 feet 4 inches across and 29 feet 11 inches long. The American machine was simply bigger in every dimension, carrying more weight, consuming more fuel, demanding more space on carrier decks. This violated every principle of Japanese naval aviation doctrine. Japanese carriers operated under severe size constraints. Hangars were smaller, elevators had limited capacity, and deck space remained at a premium. Every additional foot of wingspan meant fewer aircraft per carrier. Every extra pound of weight reduced operational flexibility. For 2 decades, Japanese engineers had optimized their fighters for compactness and lightness, creating elegant solutions to complex problems. The Americans had apparently ignored these constraints entirely. Senior engineer Watanabe opened the Hellcat's engine cowling, revealing the power plant that had propelled this fighter to dominance across the Pacific. The Pratt Whitney R-2800 double wasp filled the entire forward fuselage, its twin rows of 9 cylinders arranged in a massive radial configuration. Yamada retrieved his measuring tools and specifications notebook. Displacement, 2,804 cubic inches. The number seemed impossible. His Zero fighters used the Nakajima Sakai 12 engine, displacing just 1,700 cubic inches. The American engine was 65% larger than anything powering Japanese fighters. Watanabe consulted captured American technical manuals that intelligence services had pieced together from various sources. Rated power output, 2,000 horsepower at 2,700 RPM. The words hung in the cold morning air like an accusation. Japanese engineers had spent years trying to extract more power from their radial engines. The latest Sakai variants produced 940 horsepower. Some experimental models with improved superchargers reached 1,130 horsepower under optimal conditions. The Americans had built a production fighter engine delivering 2,000 horsepower, not as a prototype, not as an experimental test bed, as the standard power plant installed in thousands of operational fighters rolling off assembly lines at rates Japanese industry could never match. 2,000 horsepower, Yamada repeated, examining the engine's construction details. Gentlemen, if this specification is accurate, American engineers have solved fundamental problems we believed were years away from practical solutions. The double WASP's cooling system revealed the first major divergence from Japanese engineering philosophy. Each cylinder featured precisely machined cooling fins, their geometry optimized through methods that suggested sophisticated computational analysis. The fins were thinner and more numerous than anything on Japanese engines, allowing heat dissipation rates that seemed theoretically impossible. Watanabe ran his hand along the cylinder head, feeling the machining precision that had created these cooling surfaces. "These fins are not cast or forged," he announced. "They're cut directly from solid metal forgings, using automated milling processes. Every fin is identical, every cylinder is interchangeable. This represents manufacturing capability we cannot replicate." Yamada understood the implications immediately. Japanese engine production relied heavily on skilled craftsmen who hand-fitted components to precise tolerances. Each engine was essentially custom-built by experienced technicians who adjusted and modified parts until they met specifications. This approach produced excellent engines, but at speeds measured in units per month rather than units per day. The Americans had industrialized precision itself. Their cooling fins weren't better because American engineers were smarter. They were better because American factories could cut metal with automated accuracy that eliminated human error entirely. The supercharger system presented even more troubling evidence of American technological advantage. The R-2800 employed a two-stage supercharging system with automatic boost control, allowing the engine to maintain sea-level power output at altitudes exceeding 20,000 feet. Japanese supercharger development had focused on single-stage systems that provided adequate performance at medium altitudes, but lost effectiveness above 18,000 feet. Multi-stage supercharging remained largely theoretical in Japanese aviation, something discussed in engineering journals but not implemented in production fighters. The Americans had made it standard equipment. Young engineer Tanaka discovered the engine's ignition system while examining the accessory section. "Two separate magnetos," he called out. "Complete redundancy for the entire ignition system. If one fails, the engine continues operating on the second unit without any performance degradation." This redundancy philosophy appeared throughout the Hellcat's design: dual hydraulic systems, backup electrical generators, redundant fuel pumps. Every critical component had a backup system that could assume full functionality if the primary unit failed. Japanese fighters incorporated minimal redundancy, accepting single-point failures as unavoidable compromises necessary to minimize weight and complexity. When a Zero's fuel pump failed, the aircraft went down. When a Hellcat's fuel pump failed, the backup pump activated automatically, and the pilot often didn't notice until post-flight inspection. As Yamada's team continued their examination throughout January, they documented an engineering philosophy that seemed to contradict everything Japanese aviation had learned about fighter design. The Americans had built a carrier fighter that weighed 15,400 pounds fully loaded. Japanese fighters rarely exceeded 6,000 pounds. They had installed armor plating around the pilot, self-sealing fuel tanks, and structural reinforcement that added hundreds of pounds of apparently non-essential weight. The cockpit itself revealed American priorities that seemed wasteful by Japanese standards. The instrument panel contained 37 individual gauges, switches, and controls, all clearly labeled with specifications that suggested pilots required constant information about every system. Japanese fighters employed minimal instrumentation, trusting pilots to sense aircraft performance through feel and experience, rather than relying on mechanical indicators. Radio equipment occupied significant space behind the pilot's seat, providing communication capabilities that Japanese fighters had abandoned to save weight. The Americans apparently believed formation coordination through radio communication was worth the penalty of carrying heavy transmitters and receivers. Most puzzling of all was the aircraft's armament installation. 6 Browning M250 caliber machine guns, 3 mounted in each wing, with 400 rounds per gun. The combined weight of these weapons, their ammunition, and the pneumatic charging systems exceeded 800 pounds. Japanese fighters typically mounted 2 20mm cannons and 2 7.7mm machine guns, prioritizing ammunition conservation over sustained firepower. The Hellcat's guns could fire continuously for approximately 25 seconds before exhausting their ammunition supply. Japanese fighters managed perhaps 10 seconds of continuous fire before running dry. But those 25 seconds represented an enormous weight penalty that seemed to contradict every principle of efficient fighter design. Lieutenant Yamada compiled his preliminary assessment on January 28, 1945, 3 weeks after Bureau number 71,441 had arrived at Yokosuka. His report to Naval Air Technical Arsenal Command documented specifications that challenged Japanese understanding of what carrier fighters could achieve. Maximum speed, 380 miles per hour at 19,000 feet. Combat radius, 300 miles with external fuel tanks. Service ceiling, 37,000 feet. Rate of climb, 2,900 feet per minute at sea level. Every specification exceeded corresponding Japanese fighter capabilities, sometimes dramatically. But Yamada's report contained a section that troubled him more than the raw performance numbers. The puzzling aspect of American design philosophy is not that they have built a superior fighter, it is that they have built a superior fighter while apparently ignoring every principle we know to be essential for carrier aviation success. They have prioritized pilot survival over aircraft agility. They have accepted enormous weight penalties to install redundant systems. They have traded maneuverability for firepower, elegance for durability, and efficiency for operational simplicity. If this aircraft represents the future of naval aviation, then Japanese engineering doctrine requires fundamental reassessment, because by every measure we understand, this fighter should not work. Yet intelligence reports confirm it has destroyed over 5,000 Japanese aircraft in less than 2 years of combat operations. The morning of February 3, 1945, brought orders from Naval Air Technical Arsenal Headquarters. Prepare the captured Hellcat for flight testing. We must understand how Americans have achieved such dominance despite building fighters that violate our engineering principles. Yamada's team spent 3 weeks repairing battle damage and restoring Bureau number 71,441 to airworthy condition. The engine had suffered minor damage during the emergency landing, requiring replacement of several cylinders and complete reassembly of the accessory drive section. Spare parts proved scarce. American aircraft components didn't match Japanese manufacturing standards or metric specifications. Every replacement part required custom fabrication or careful modification of available materials. The landing gear system demanded extensive repairs, its hydraulic components damaged beyond simple fixes. Japanese engineers reverse-engineered the actuating mechanisms, creating replacement parts from available steel alloys that approximated American specifications. On February 27, 1945, Test Pilot Commander Sato conducted the first Japanese evaluation flight of an American Hellcat fighter. He taxied the repainted aircraft, now bearing tail code YO801 of the Yokosuka Kokutai, to the runway threshold. The massive Pratt Whitney radial produced a deep, powerful rumble, completely unlike the higher-pitched note of Japanese engines. Sato advanced the throttle, feeling 2,000 horsepower press him back into the armored seat as the Hellcat accelerated down the runway. The fighter climbed away from Yokosuka at rates that exceeded any Japanese fighter Sato had flown, the R-2800 delivering power that seemed excessive for any practical combat requirement. At 10,000 feet, he began basic handling evaluations, exploring the Hellcat's flight characteristics, with the caution of a pilot flying enemy equipment for the first time. The controls felt heavy compared to Zero fighters. Aileron response required significant stick force to initiate rolling maneuvers. The rudder pedals demanded considerable effort to coordinate turns properly. Japanese fighters employed light, responsive controls that allowed pilots to make precise adjustments with minimal input. The Hellcat's heavy controls suggested American pilots were physically stronger, or that American design philosophy accepted reduced control sensitivity in exchange for some other benefit. Sato attempted a standard combat maneuver, pulling the Hellcat into a tight climbing turn that would have been routine in a Zero fighter. The American fighter responded sluggishly, requiring nearly twice the turning radius to complete the same maneuver. Its heavier weight and less efficient aerodynamics prevented the kind of agile dogfighting that Japanese pilots had perfected. This should have been a fatal flaw. Japanese combat doctrine emphasized turning performance above all other fighter characteristics. Victory in aerial combat came to the pilot who could outturn his opponent, positioning for a killing shot while the enemy struggled to bring guns to bear. The Hellcat couldn't win this kind of fight. At 15,000 feet, Sato tested high-speed performance, pushing the throttle forward to maximum continuous power. The Pratt Whitney responded smoothly, the supercharger maintaining boost pressure as the fighter accelerated to speeds that exceeded anything Japanese fighters could achieve in level flight. The airspeed indicator climbed past 300 miles per hour, then 350, finally stabilizing near 375 miles per hour at 17,000 feet. This speed advantage suggested a different kind of aerial combat, one where Japanese pilots couldn't force American fighters into turning engagements because the Americans could simply refuse to fight, using superior speed to disengage whenever tactical conditions weren't favorable. Sato's test report landed on Yamada's desk on March 1, 1945. The evaluation contained observations that confirmed the engineer's suspicions about American design philosophy. The captured Hellcat cannot match Zero fighters in turning performance or low-speed maneuverability. However, it demonstrates significant advantages in maximum speed, climb rate at altitude, and sustained high-speed flight. Most importantly, the aircraft remains controllable and effective even when subjected to combat damage that would destroy Japanese fighters. During landing trials, I deliberately performed a hard carrier-style approach that would normally damage our fighters' landing gear. The Hellcat absorbed the impact without apparent structural stress. American pilots flying this aircraft can afford to make mistakes that would kill Japanese pilots. They can absorb battle damage that would down our fighters. They can maintain combat operations with mechanical failures that would force us to abandon aircraft. The Hellcat's superiority derives not from better aerodynamics or more elegant engineering, but from brute force solutions to combat problems that we have tried to solve through precision and efficiency. Yamada understood what Sato's report meant. American engineers hadn't discovered new principles of aerodynamics or revolutionary theories of aircraft design. They had simply decided that pilot survival mattered more than aircraft performance, that redundancy was worth its weight penalty, and that combat effectiveness meant building fighters that could take punishment and keep flying. Japanese fighters optimized every gram of weight, every square inch of drag, every possible efficiency. American fighters accepted massive inefficiencies in exchange for operational capabilities that Japanese doctrine had dismissed as unnecessary. The question that haunted Yamada as he reviewed Sato's evaluation was simple and terrible. What if American doctrine was correct? If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. What if the elegant solutions Japanese engineers had perfected over decades were actually wrong? What if the future of aerial warfare belonged to heavy, durable, powerful fighters that sacrificed agility for firepower, efficiency for survivability? The answer was already written in the combat statistics accumulating across the Pacific. Hellcat pilots were destroying Japanese fighters at ratios that made mockery of the principle that superior maneuverability determined air combat outcomes. American pilots didn't need to outturn Zero fighters. They simply dove from altitude, used superior speed to make high-deflection shooting passes, and climbed away before Japanese pilots could respond. If a Zero pilot managed to get on a Hellcat's tail, the American could dive away at speeds Japanese fighters couldn't match. If a Zero damaged a Hellcat, redundant systems and heavy armor kept the American pilot alive long enough to return to his carrier. The most telling detail in Sato's report was the landing gear observation. Japanese fighters required skilled pilots who understood the aircraft's structural limitations. One hard landing could bend the gear struts, requiring extensive repairs. The Hellcat was designed for average pilots making routine mistakes. Its landing gear could absorb punishment that would destroy Japanese fighters, allowing less experienced pilots to survive their early missions and gradually develop the skills that turned novices into veterans. This democratization of aviation excellence represented American industrial philosophy at its most fundamental. Japanese fighters demanded exceptional pilots to achieve their full potential. American fighters allowed average pilots to survive long enough to become exceptional. By March 1945, Yamada's team at Yokosuka had completed their evaluation of Bureau number 71441. The captured Hellcat had revealed American engineering philosophy with devastating clarity. They had solved the problem of pilot attrition not through better training or superior tactics, but through better aircraft that protected pilots from their own mistakes and from enemy fire. They had answered the challenge of carrier aviation not by building smaller, lighter fighters, but by building larger carriers with more powerful catapults and stronger arresting gear. They had addressed the weight penalty of armor and redundancy not by finding lighter materials, but by installing engines powerful enough to compensate for the extra pounds. Every solution required industrial capabilities that Japan simply didn't possess. The precision manufacturing that made the R-2800's cooling fins, the production capacity that delivered thousands of fighters monthly, the metallurgical expertise that created armor plating light enough for fighters, yet strong enough to stop machine gun bullets. The hydraulic systems are sophisticated enough to operate redundant controls without adding prohibitive complexity. Yamada's final report to Naval Air Technical Arsenal Command contained conclusions that read like an epitaph for Japanese naval aviation doctrine. We have successfully evaluated the captured F6F Hellcat and determined that American engineers have not discovered revolutionary new technologies or principles. They have simply applied industrial capabilities we cannot match to solve combat problems we believed required elegant engineering solutions. The Hellcat succeeds because America can afford to build 15,000-pound fighters when we can only build 6,000-pound fighters. They can install 2,000 horsepower engines when we can only install 1,000 horsepower engines. They can accept massive inefficiencies because their industrial base can overcome inefficiency through sheer productive capacity. Most troubling of all, their design philosophy proves correct in combat. Superior durability defeats superior agility. Redundant systems defeat lighter weight. Firepower defeats maneuverability when pilots can't be forced into turning engagements. On April 8, 1945, Commander Sato attempted another test flight in the captured Hellcat. The Pratt Whitney R-2800 suffered a mechanical failure during climb-out, its complex supercharger system experiencing problems that Japanese maintenance crews couldn't diagnose with available tools and parts. Sato performed an emergency landing, bellying the Hellcat back onto Yokosuka's runway with the kind of controlled crash that would have destroyed most Japanese fighters. Bureau number 71441 absorbed the impact, its heavy structure and reinforced belly taking punishment that proved the American design philosophy one final time. The aircraft could no longer fly. Japanese engineers lacked the spare parts, technical documentation, and manufacturing capabilities to repair the sophisticated American engine. The Hellcat was pushed to a dispersal area and abandoned, its brief service in Japanese markings ending with mechanical failure that highlighted the technological gap no amount of analysis could bridge. When American forces occupied Yokosuka Naval Air Base in August 1945, they discovered the captured Hellcat sitting in tall grass, its paint faded, Hinamaris peeling, tail code Yo801 still visible on the vertical stabilizer. The aircraft that had once terrorized Japanese pilots now served as a monument to industrial warfare's harsh arithmetic. American ground crews examined their own fighter with interest, noting the Japanese repairs and modifications that revealed desperate attempts to understand technology they couldn't replicate. The Hellcat's data plate still showed Bureau number 71441, squadron designation VF-44, USS Langley. The fighter had traveled from American carrier, decks to enemy testing facilities, and back to American hands, its journey documenting the gap between elegance and effectiveness. Lieutenant Charles August survived 9 months as a prisoner of war in a camp near Tokyo, enduring conditions that tested limits he hadn't known existed. He emerged in September 1945, gaunt and weakened but alive, one of the fortunate few who survived Japanese captivity. His Hellcat had protected him through 42 combat missions before mechanical failure forced him down over enemy territory. The fighter's rugged construction had given him a survivable crash landing. Its presence at Yokosuka had given Japanese engineers a glimpse of American industrial philosophy. But Bureau number 71441 could not protect August from 9 months behind barbed wire. The story of this single captured Hellcat illuminated a larger truth about the Pacific War's aerial campaign. Japanese engineers at Yokosuka had correctly diagnosed every technical detail of American aviation superiority. They understood the power output advantage. They recognized the importance of redundant systems. They appreciated the value of armor protection and self-sealing fuel tanks. Understanding, however, proved worthless without the industrial capacity to implement solutions. Japan's aviation industry in 1945 bore little resemblance to the confident enterprise that had produced the legendary Zero fighter in 1940. Raw material shortages crippled production. Allied bombing raids destroyed factory capacity faster than it could be rebuilt. Skilled workers had been drafted into military service, replaced by inexperienced laborers who couldn't maintain pre-war quality standards. Even if Japanese engineers had designed a fighter incorporating every lesson learned from the captured Hellcat, the industrial base needed to build such aircraft no longer existed. American production numbers told the story in mathematics that admitted no counter-argument. Grumman's Bethpage plant produced over 12,200 Hellcats between October 1942 and November 1945. Peak production reached 500 fighters per month, a rate that exceeded Japan's total monthly aircraft production across all types and manufacturers. Every day, American factories delivered approximately 17 new Hellcats to the Navy, while Japanese factories struggled to complete 17 fighters of all types per week. The Pratt Whitney R-2800 engine that had so impressed Yamada's team at Yokosuka represented just one piece of America's industrial miracle. Over 125,000 double Wasp engines were manufactured during the war years, powering not only Hellcats, but also Corsairs, Thunderbolts, and dozens of other aircraft types. Japanese industry never built 125,000 engines of any type during the entire war. The cooling fin manufacturing technology that Japanese engineers found so remarkable was just standard practice in American factories. Automated milling machines cut precise fin geometries with tolerances measured in thousandths of an inch, producing identical components at rates measured in minutes per unit rather than hours per unit. Japanese craftsmen could hand-cut cooling fins approaching American quality standards, but they required days to accomplish what American machines completed in minutes. This productivity gap meant that even if Japanese designs matched American technical sophistication, production rates would remain hopelessly outmatched. The supercharger systems that gave the R-2800 its high-altitude performance required metallurgical expertise that Japanese industry couldn't replicate. American steel mills produced specialized alloys designed for specific temperature and stress conditions. Turbine wheels spinning at 22,000 revolutions per minute demanded materials that could maintain structural integrity under centrifugal forces that would tear apart conventional steel. Japanese metallurgists understood the theory behind these specialized alloys. They could analyze captured American materials and identify the precise chemical compositions. But understanding composition differed fundamentally from possessing the industrial processes to manufacture those materials in production quantities. American steel mills processed tonnage. Japanese foundries processed batches. The redundancy philosophy that characterized Hellcat design extended far beyond individual aircraft systems to the entire American industrial infrastructure. If one factory suffered damage, production shifted to other facilities. If one supplier failed to deliver components, alternate suppliers filled the gap. If one shipping route became dangerous, cargo moved through different ports. Japanese industry operated with minimal redundancy, accepting that disruptions would cascade through the entire production system. When American submarines sank ships carrying raw materials from Southeast Asia, Japanese factories had no alternate supply sources. When B-29 bombers destroyed a critical manufacturing plant, no backup facility existed to absorb its production. Every vulnerability became catastrophic because the industrial system lacked the resilience that redundancy provided. The pilot training pipeline revealed similar disparities. American naval aviation maintained a vast training infrastructure that produced thousands of qualified fighter pilots annually. Training facilities across the United States taught identical curricula using standardized methods. If a pilot died in combat, 5 more graduates stood ready to replace him. Japanese pilot training had emphasized quality over quantity, producing small numbers of highly skilled aviators through intensive programs that took years to complete. When these elite pilots died in combat, as they inevitably did, Japan lacked the training capacity to replace them at anywhere near the required rate. By 1945, Japanese fighter squadrons included pilots with only 50 hours of total flight time, facing American opponents with 200 hours of training before ever seeing combat. The captured Hellcat at Yokosuka had demonstrated that American fighters were designed for these less experienced pilots. Heavy controls prevented overly aggressive maneuvering that might stress the airframe beyond design limits. Redundant systems meant mechanical failures rarely caused crashes. Armor protection gave pilots multiple chances to learn from mistakes that would have killed Japanese aviators in their first combat. This design philosophy extended to maintenance procedures as well. Hellcat engines were designed for removal and replacement by relatively unskilled personnel using simple tools. Modular construction meant that damaged components could be swapped out rather than repaired, reducing maintenance time from days to hours. Japanese fighters required skilled mechanics who understood complex systems and could hand-fit replacement parts to precise tolerances. When those mechanics became casualties or were transferred to other duties, fighter squadrons lost their maintenance capabilities, even when they had plenty of aircraft and pilots. The tactical implications of these industrial and design differences became apparent in every air battle after mid-1943. Japanese pilots flying lightweight, maneuverable Zeros found themselves unable to force Hellcat pilots into the turning fights where Japanese advantages mattered. American pilots simply refused to turn, using superior speed and altitude performance to dictate engagement terms. When Japanese pilots damaged Hellcats, the American fighters often survived long enough to return to their carriers. When American pilots damaged Zeros, the lightweight Japanese fighters usually went down immediately, their lack of armor and self-sealing tanks making them vulnerable to hits that Hellcats could absorb. The statistical result was the 19-to-1 kill ratio that characterized Hellcat combat performance. For every Hellcat lost in air-to-air combat, Japanese losses approached 19 aircraft. This ratio wasn't sustainable for any military force, but particularly not for Japan's shrinking pilot pool and declining industrial capacity. The Battle of the Philippine Sea in June 1944 demonstrated American aviation supremacy with mathematical brutality. Over 2 days of combat, Hellcat pilots from Task Force 58 shot down more than 600 Japanese aircraft while suffering fewer than 30 losses. American sailors dubbed the engagement the Great Marianas Turkey Shoot, a nickname that captured the one-sided nature of the slaughter. Japanese pilots attacked in waves, their training limited, their aircraft outperformed, their tactics outdated. Hellcat pilots intercepted them at altitude, dove through the formations with superior speed, and shot down aircraft that couldn't maneuver away or survive the devastating firepower of 12 50 caliber machine guns. The few Japanese pilots who managed to engage Hellcats in dogfights discovered that even when they achieved favorable positions, their 7.7mm machine guns and 20mm cannons lacked the hitting power to bring down heavily armored American fighters before the Hellcats could disengage. Lieutenant Yamada at Yokosuka received intelligence reports from the Philippine Sea battle in July 1944, 6 months before the captured Hellcat would arrive for his evaluation. The reports contained detailed accounts from surviving Japanese pilots, their testimony documenting the hopelessness of fighting an enemy with overwhelming advantages in every dimension that mattered. One pilot reported, "I achieved a perfect firing position on an American AT's fighter. My cannons struck the fuselage repeatedly at ranges where Zero fighters would have exploded. The American aircraft continued flying, climbed away, and I could not follow due to my damaged engine." Another survivor described attacking Hellcat formations. "They did not turn to fight us. They maintained formation and increased speed. We could not catch them. When we broke off to seek easier targets, they returned and shot down 3 of my squadron mates before we could respond. The pattern repeated in every engagement. Japanese pilots fighting with courage and skill, employing tactics that had worked brilliantly in 1942, discovering that by 1944, those tactics were suicide against an enemy whose fighters embodied industrial philosophy they couldn't match. By the time Bureau number 71441 arrived at Yokosuka in January 1945, the question wasn't whether Japanese engineers could understand American aviation superiority. Yamada's team understood perfectly. The question was whether understanding mattered when Japan lacked the industrial capacity to implement solutions. The answer was written in production statistics, combat loss ratios, and the steady contraction of Japanese-controlled territory as American forces advanced across the Pacific. Yamada's engineering reports documented technical specifications and design philosophies with precision that would have been valuable in peacetime, when Japan could have studied American methods and gradually adapted its own industry to match American capabilities. But in wartime, with Japan's industrial base crumbling under Allied bombing and submarine blockade, the reports served mainly as evidence of how thoroughly Japan had lost the industrial war that determined the outcome of the shooting war. The Hellcat's Pratt Whitney R-2800 engine represented decades of American investment in aviation technology, metallurgy, precision manufacturing, and industrial process development. Japanese industry couldn't replicate this engine in 1945 any more than it could build the automated factories that produced it or train the workforce that operated those factories. The 6 Browning 50 caliber machine guns mounted in the Hellcat's wings represented American industrial capacity to manufacture precision weapons in quantities that exceeded Japanese ammunition production for comparable weapons. Each Hellcat carried 2,400 rounds of 50 caliber ammunition, more than the total ammunition load of 3 Zero fighters. Japanese pilots rationed their ammunition, firing short bursts to conserve limited supplies. American pilots could hold triggers down for extended engagements, trusting that their carriers held vast reserves of replacement ammunition. This abundance mentality pervaded American military operations at every level. Damaged fighters were often pushed overboard to make deck space for new aircraft, because replacement fighters arrived faster than repair facilities could restore damaged ones. Japanese mechanics worked miracles keeping damaged fighters operational because no replacements existed. American carriers operated with spare parts inventories that exceeded the total parts production of Japanese aviation industry. When a Hellcat needed a new propeller or replacement landing gear, the parts were available immediately. When a Zero needed similar components, mechanics cannibalized other aircraft or fabricated replacements from whatever materials they could scavenge. The fuel situation illustrated the resource disparity with particular clarity. Each Hellcat required approximately 250 gallons of aviation gasoline for a standard combat mission. Task Force 58 consumed fuel at rates measured in thousands of gallons per hour, supplied by a logistics train that stretched back to American refineries processing crude oil from Texas, California, and Oklahoma. Japanese forces in 1945 operated under fuel restrictions so severe that pilots often received less than 20 gallons for training flights. Many aircraft sat grounded, not due to mechanical problems, but simply because no fuel existed to operate them. The Yokosuka test program for the captured Hellcat consumed more aviation gasoline than some frontline Japanese fighter squadrons received in a month. When American occupation forces discovered Bureau number 71441 in August 1945, they found Japanese maintenance logs documenting the test flights. The logs revealed that Japanese engineers had conducted fewer than 10 hours of flight testing over 2 months, limited not by lack of interest but by lack of fuel. American test programs routinely logged hundreds of hours, evaluating new aircraft variants. Fuel consumption, never a consideration. The technological assessment that Yamada completed in March 1945 circulated through what remained of Japanese Naval Aviation Command. Senior officers read the reports with resignation, understanding that the captured Hellcat's lessons arrived far too late to matter. Even if Japanese industry could have implemented American design philosophies, even if fuel and materials had been available, even if skilled workers could have been found, production timelines meant new fighters wouldn't enter service before the war's inevitable conclusion. Some younger engineers at Yokosuka proposed a desperate program to copy the Hellcat directly, reverse engineering American solutions, and adapting them to Japanese production capabilities. The proposal died in preliminary planning stages when material specialists calculated raw material requirements. Building even one Hellcat equivalent prototype would consume aluminum allocations intended for 10 conventional fighters. The high-strength steel needed for landing gear and structural reinforcement wasn't available in required quantities. The specialized alloys for a 2,000 horsepower engine existed only in captured American aircraft. Japan's aviation industry in early 1945 was attempting to produce fighters using aluminum alloyed with sawdust as a substitute for materials that were no longer available. Engines were built with inferior steel that reduced operating lifetimes by 70%. Lubricants were synthesized from pine resin when petroleum-based oils became unavailable. Under these conditions, discussing programs to build American-style fighters was worse than futile. The engineers who had hoped technology might provide solutions confronted the reality that war was ultimately about industrial capacity, resource access, and production efficiency. Japan had lost this war not on Pacific battlefields but in American factories that outproduced Japanese industry by margins approaching 10-1. Commander Sato, the test pilot who flew the captured Hellcat, survived the war and returned to civilian life in a Japan devastated by 4 years of conflict. He occasionally thought about his brief flights in the American fighter, remembering the sensation of having 2,000 horsepower at his command, feeling controls that assumed the pilot might make mistakes and incorporated redundancy to prevent those mistakes from becoming fatal. He thought about his comrades who had died flying elegant, efficient, deadly Zero fighters that couldn't absorb battle damage and couldn't protect their pilots from the consequences of combat. He wondered what Japanese aviation might have achieved if industrial capacity had matched engineering skill. But that was fantasy. The reality was that Japan had built the fighters its industry could produce with available resources, and those fighters had been adequate when facing opponents with similar limitations. When facing an opponent whose industrial capacity was effectively unlimited, whose resources included an entire continent's raw materials, whose production efficiency reduced manufacturing time from months to weeks, elegance and efficiency proved inadequate. The captured Hellcat at Yokosuka had taught Japanese engineers that American aviation superiority wasn't mysterious or based on revolutionary breakthroughs. It was the straightforward result of industrial philosophy that prioritized abundance over efficiency, reliability over elegance, and combat effectiveness over theoretical optimization. America could afford to build heavy fighters because American factories could produce engines powerful enough to fly heavy fighters. America could accept redundancy because American production rates meant that weight penalties didn't reduce total fleet size. America could armor its fighters because American metallurgy could produce armor plate, and American pilots survived to apply lessons learned because armor kept them alive through early mistakes. Japan couldn't afford any of these solutions, not because Japanese engineers were less skilled or Japanese pilots less brave, but because Japanese industry couldn't match American productive capacity at any level that mattered. The final irony was that Bureau number 71441, the specific Hellcat that Japanese engineers studied so carefully, represented nothing special in American production. It was one of 12,275 identical fighters built to identical specifications, powered by engines from a production run exceeding 125,000 units. When this particular fighter was lost over Formosa, the Navy didn't notice. Another Hellcat immediately took its place, flown by another pilot from an apparently inexhaustible pool of trained replacements. Lieutenant Charles August, who flew this fighter on 42 missions before mechanical failure forced him down, was valuable. The Navy made efforts to rescue him, though they failed. But the fighter itself was merely one interchangeable unit in a vast fleet. Its loss mattered only statistically, as a single data point in combat loss reports that tracked thousands of aircraft across dozens of carrier air groups. This disposability was perhaps the most American characteristic of all. Build enough of anything that individual units become expendable. Train enough pilots that casualties don't deplete capabilities. Produce enough ammunition that conservation isn't necessary. Supply enough fuel that consumption rates don't constrain operations. Japanese aviation operated under the opposite philosophy. Every aircraft was precious because production couldn't replace losses. Every pilot was irreplaceable because training pipelines couldn't fill gaps. Every gallon of fuel was rationed because supplies were critically limited. Every round of ammunition was carefully managed because production couldn't keep pace with consumption. These constraints shaped doctrine, tactics, training, and aircraft design in ways that created fundamental disadvantages against an opponent operating without similar limits. The story of the captured Hellcat at Yokosuka ended in August 1945, with American forces finding their own fighter bearing Japanese markings, pushed aside after mechanical failure. Its brief service as enemy evaluation aircraft concluded. But the larger story, the story of industrial warfare determining military outcomes regardless of tactical brilliance or individual courage, continued long after the war ended. American aviation dominance in the Pacific didn't result from superior pilots or better tactics, though American pilots were well trained and American tactics were effective. It resulted from building more fighters, training more pilots, and supplying both with resources that seemed unlimited compared to Japanese capabilities. The Hellcat's 19-to-1 kill ratio reflected this industrial advantage as much as any technical superiority. American pilots could engage Japanese fighters with confidence because even if they died, their squadron would receive a replacement pilot and fighter within days. Japanese pilots flew knowing that their loss would create a gap that might never be filled. American pilots could burn through ammunition in long bursts because resupply was certain. Japanese pilots rationed ammunition because resupply was unlikely. American pilots could risk battle damage because redundant systems kept damaged fighters flying. Japanese pilots knew that serious damage meant death because their fighters lacked protection. These psychological factors mattered as much as technical specifications. Combat effectiveness came from knowing you could make mistakes and survive, knowing you had backup systems if something failed, knowing that if you went down, your squadron would continue operations without missing a beat. Japanese pilots in 1945 knew none of these things. They knew they flew fighters that couldn't match American performance. They knew their training was inadequate. They knew that if they died, their loss weakened Japan's already depleted forces. They knew they were fighting an enemy who could replace losses faster than Japan could inflict them. This knowledge affected combat performance in ways that no amount of courage could overcome. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The captured Hellcat at Yokosuka Naval Air Technical Arsenal stood as a monument to industrial warfare's brutal mathematics. Japanese engineers had successfully analyzed American aviation superiority and understood every technical detail that contributed to Hellcat dominance. Understanding, however, proved worthless without industrial capacity to implement solutions. Japan had lost the Pacific Air War not because its engineers failed to comprehend American advantages, but because comprehension without capability changes nothing. Bureau number 71441 had traveled from American carrier decks to enemy test facilities and back to American hands, its journey documenting the gap between theoretical knowledge and practical implementation. The fighter represented not revolutionary technology but revolutionary productive capacity, not engineering genius but industrial philosophy, not mysterious superiority but straightforward abundance applied systematically across every dimension of military aviation. The lesson Japanese engineers learned from this captured fighter was simple and terrible. Wars are won in factories, not in cockpits.